Section 3.3, we're going to kind of take everything that we learned in Section 3.2 and put it all together now and look at analyzing the graph of a rational function. With rational functions, the first thing you want to do is factor. If there's anything that can be reduced or factored, go ahead and do that, because that will help you spot either x-intercepts, y-intercepts, holes, vertical asymptotes, all of that good stuff. Once you're given a function, you want to factor that function. So if we factor this function right here, what are we going to get in the denominator? X plus 2x minus 2. So we've done step 1 for this function. Step 2 is to write that function in its lowest terms. Well, it is, because we don't have any factors that will reduce. Then we locate the intercepts of the graph and determine the behavior of the graph near each x-intercept using the same procedure as for polynomial functions. So we can go ahead and do that. Where is our x-intercept going to be? How do you find an x-intercept? It's where the y is equal to 0, right? So if we set the y value equal to 0, meaning this function here is equal to 0, the only way for a fraction to be equal to 0 is if the numerator is equal to 0, not the denominator. So the only way this numerator is equal to 0 is if x is equal to 1. So that's your x-intercept. How do we get our y-intercept? Let x be 0. So our y-intercept is going to occur at 0. Negative over a negative is positive 1/4. Step 4, locate the vertical asymptotes and graph each vertical asymptote using a dashed line. So here's our vertical asymptotes at -2 and 2, and we're using a dashed line. We have vertical asymptotes at x equals plus or minus 2. Step 5 says to locate the horizontal or oblique asymptotes. Which will we have here, horizontal or oblique? Horizontal. So we have a horizontal asymptote where? At y equals 0. The x-axis is a horizontal asymptote because the degree of the numerator is 1, the degree of the denominator is 2. And you don't need to sketch it in if you just know, or maybe extend it out so that you can see. And then step 6 says use the zeros of the numerator and the denominator of r to divide the x-axis into intervals, determining where the graph is above or below the x-axis by choosing a number within each interval and evaluating r there, and then plot the points as found. So what we do here is we take our x-axis. This is the real number line. It goes from -infinity to infinity. We had critical points is what we're going to call them, at asymptotes at -2 and at 2, and we had an x-intercept here at 1. So anywhere the numerator is 0 or the denominator is 0, those are going to be points at which we're going to want to divide this into intervals. So then we just pick any point in that interval. Here's our intervals that go from -infinity all the way to infinity. Pick a number, any number will work. Plug it into the function in place of x. So if we let x be -3, let's go back up and look at our function. If x is -3, then that's going to give us with -4/5. Because this number is negative, then that means that the graph will be below the x-axis everywhere in that interval. But we also have a point on the graph that we can plot. The point is -3, -0.8, or -4/5. Remember, this is the x value, this is the y value that we get. And then we go on and just pick points within each interval. Let x be 0, we've got another point, happens to be our y-intercept. Let x be 3/2, then you get another point. Let x be 3. Did we have to use 3/2 here? No, I just had to pick a number between 1 and 2. I mean, I could have used 16/15. You know, it's just that that would be the nicest number I could use between 1 and 2. Any number in this interval will work. Because this is negative, that means that in this interval, every number is going to be negative between 1 and 2. And then from 2 to infinity, we can pick another number, and they selected 3. So what that does is it gives us more points that we can plot. Then we analyze the behavior of the graph near each of the asymptotes. When we do that, we want to know, is it going off to infinity? Is it approaching -infinity? How can we tell? Short of grabbing our graphing calculators, how can we tell what the behavior of the function is going to be over here or over here? We know that between -infinity and -2, the graph is going to be negative. We also know that the graph can't cross over this vertical asymptote. So can't we just kind of reason that if it's going to be negative, then it's going to be going down along here and approach that asymptote? And isn't the x-axis also a horizontal asymptote? So as we go off, just using reason here, can't we tell that this is going to go that way? If this is the behavior of the graph at this point, can't I reason that at some point we have to cross through the y-axis without dipping down into the negative region? And then at some point, if I kept going like this, I would cross the vertical asymptote. It can't do that shape. It's got to go eventually up along that asymptote. What I could do is I could pick some more points to plot closer to x equals -2 and see that as x gets closer and closer to -2 from the right, I'm going to be going off to positive infinity. What do you think is going to happen here? It's going to go down towards negative infinity. And then what's happening here is x goes to the left. Is it going to do this? No. It's going to go up and approach that vertical asymptote. And then what about going down? Is it going to go down like that? No, why not? We have a horizontal asymptote here. Don't forget about your horizontal asymptote. The graph is going to approach that value there. Now, we can always take our graphing calculators and double check that graph and make sure that that looks reasonable. And if we zoom in and let our window go from, I don't know, -5 to 5, you should see a graph that looks fairly similar to this. So here is the summary then of the steps that we went through to analyze the graph of the function. Now let's just do one on our own. We want to analyze the graph of this rational function. What should we do first? Simplify. What do you mean by simplify? I agree, simplify. Okay, let's factor it. So this is going to give us x plus 1 times x minus 1 over x. What do we know about the x-intercepts? To find the x-intercepts, we set the numerator equal to 0, and we have x-intercepts at plus or minus 1. What about y-intercepts? We have no y-intercept. How do we find y-intercepts in general? Let x be 0. What happens if x is 0? The denominator is 0. Well, what does that tell us about the denominator? Is a vertical asymptote. No y-intercept. We have a vertical asymptote at x equals 0. That's the y-axis. Is there a horizontal asymptote? Since we're talking asymptotes here. No, there's not a horizontal asymptote. What is there? We have an oblique. How do we determine where our oblique asymptote lies? We divide this by x. We're dividing the numerator by x, because x is in the denominator. So when we divide this out, x goes into x squared, x times x is x squared, x, then that's all we need to do. So then we can subtract, and we get no x's, and we get minus 1. So this looks like this is going to be x minus 1 over x. But typically you want to fill in the missing powers of x with a 0 in front of it. But anyway, this is going to reduce. So we have an oblique asymptote at y equals x, because it's just the part that's not the fraction. Now what? This is the point at which we would divide the number line into intervals. So we're going to take a number line here, and I'm going to divide it into intervals at my asymptotes and my intercepts. So this first interval is going to go from negative infinity to what? -1. And then I'm going to go from -1 to 0, because I have a vertical asymptote there, and 0 to 1, and then 1 to infinity. Now we pick a test point. Let's test x equals, what's the number in this interval? -2. So look at r of -2. What is r of -2? -3/2. So the graph is going to be below the x-axis there. That means that the graph is below the x-axis. And we have what point on the graph? -2, -3/2. Then from -1 to 0, what point do we want to use? -1/2 works for me. So we have -1/2 squared minus 1 divided by 1/2, and we get r of -1/2 is equal to what? This is why God gave us calculators. +3/2. So now that means that we have the point -1/2, +3/2 on the graph. So the graph is going to be above the x-axis between -1 and 0. And then what about from 0 to 1? What do we want to test here? 1/2. R of +1/2 is negative 3/2. So the graph is below the x-axis again, and we have the point 1/2, negative 3/2 on our graph. And here we want to test what? 2 works, 2 million works as well, but r of 2 is easier to find. R of 2 is 3/2. So we have the point 2, 3/2 on the graph. So now we're ready to take some information that we have, put it together, and graph the function, I believe. We're ready for that. Here's our graph. So we have some points that we can plot that are on the graph. What points can we plot? Negative 2, negative 3/2, negative 1/2, positive 3/2, 1/2, negative 3/2, and 2 3/2. What about our asymptotes? We have asymptotes at x equals 0. So we have a vertical asymptote here. We also have an oblique asymptote at y equals x. Here's the graph of y equals x. And we have intercepts where? At 1 and negative 1. So we've got points here and here. Can we connect the dots now and graph this function? I think so. Looking at our asymptotes, it looks like our graph is going to go something like this, keeping the asymptotes in mind. Check the end behavior the function behavior at the intercepts. We can, it's possible, but I think on this problem we had enough information that we could draw a fairly decent shape without going to that added difficulty, just based on the information that we were given. Analyzing the graph of this rational function. First thing we need to do is what? Simplify. Well, that numerator doesn't factor, does it? Then what? Intercepts. Are there any x-intercepts? Nope. Graph doesn't cross the x-axis because that numerator is never going to be equal to 0. Are there any y-intercepts? No, because the graph is never going to be equal to 0. Where do we go if there's no intercepts? Asymptotes. If there's no intercepts, there's got to be asymptotes somewhere. And I think there's asymptotes in a lot of places. First of all, vertical asymptote. Vertical asymptote occurs at x equals 0. Is there a horizontal asymptote? No, because the degree of the numerator is greater than the degree of the denominator. No horizontal. What about oblique? It's not called an oblique. It's only called an oblique asymptote if the asymptote is linear. But there is asymptotic behavior, and that behavior is going to be along a quadratic. So there is asymptotic behavior. Asymptotic behavior is considered quadratic. If we were to divide x to the 4th plus 1 by x squared, what would we get? And we would subtract this, and we would get the 1, and we get x squared plus 1 over x squared. So when we go to draw the graph or sketch the graph of this function, we would have precious little to work with. Vertical asymptote right here, and we would have a quadratic asymptotic behavior right here. And then how would we get points to plot? Just start plugging points into the function. So we need to start plotting some points. So we have, if x is equal to 1, what is y equal to? 2. If x is equal to negative 1, what is y equal to? 2. I think that's enough to get us going here. If x is 1, we have a point at 2. If x is negative 1, we have a point at 2. Fairly confident that we can sketch our graph in like so. So our graph would look something like this. And this asymptotic behavior right here is at x equals 0 and at y equals x squared. But we don't call it an oblique unless it's a linear asymptote. And to be more precise, you could sketch more points in. One last example, and then we got to look at an application problem. Let's analyze the graph of this rational function. First of all, we need to do what? Factor it. So that's going to give us 2x minus 1 times x minus 2 over x plus 2 times x minus 2. So where are our x-intercepts? Negative 1/2, x equals negative 1/2. No, not negative, positive 1/2. What about a y-intercept? Not at x equals 2, because that's going to cancel and that's going to leave us what? It's going to have a hole at x equal 2. And it has the hole because these here could cancel out. Alright, so we have a y-intercept at negative 1/2. Do we have any vertical asymptotes where the denominator is equal to 0? Do we have a horizontal asymptote? Not at x equals, but at y equals 2. Why is it 2? The degrees are the same, so it's leading coefficient over leading coefficient. That's 2 over 1. Can I be more precise here with where the hole is? I know it's located at x equals 2, but what is the y value going to be when x is 2? Let's find f of 2 whenever our function is 2x minus 1 over x plus 2. F of 2 is going to be 3/4, is it not? So we have a hole, we could be more precise, at the point 2 3/4. So putting all this together then, we can sketch in our graph. What points can I plot? X equals 1/2, y equals negative 1/2. We have a hole at 2 3/4, so we have a hole right there. And we have asymptotes at x equals negative 2 and y equals positive 2. So when we sketch in our graph, go to sketch in our graph, we know that our function is going to have this behavior and become asymptotic here. And it's also going to go over here and become asymptotic. I need to just plot a point on this side to get that piece, but I got this piece very well. It is a break. It's actually a gap. You could fill in that gap with a point, but it's there. It's just hard to see if you're using a graphing calculator. I can exaggerate the hole right there on the graph when I draw it, but on the calculator it would look continuous. But there really is a break right there. Alright, the last example is how to minimize the cost of producing a can. We're told that the Reynolds Metal Company manufactures aluminum cans in the shape of a cylinder with a capacity of 500 cubic centimeters, which is a half a liter. The top and bottom of the can are made of a special aluminum alloy that costs a nickel per square centimeter. The sides are made of an alloy that costs 2 cents per square centimeter. So what we want to do here then in part A is express the cost of the material for the can as a function of the radius of the can. So the cost of the material of the can for the top and the bottom is going to be the area, or the surface area of the can for the top and the bottom. We have two, the top and the bottom, that are going to be pi r squared, because the area of a circle is pi r squared. The cost is a nickel per square centimeter, so we're going to put our nickel right here. And then when we flatten out this can, this lateral surface area, the sides of the can, is going to be the same as the circumference of this circle, which is 2 pi r, and then times the height. So it's the length times the width of the rectangle, but the length of that rectangle is 2 pi r. So that's the area of the side, and then it costs us 2 cents. To express the cost as a function of the radius, we would have this function right here. C of x, 2 pi r squared times 0.05. What is 2 times 0.05? 0.1? We'd have 0.1 pi r squared plus 0.04 pi r h. Now we need to get the height in terms of the radius. We want to have this strictly as a function of the radius of the can. So that means that we've got to figure out what the height is in terms of the radius. I'm sorry, there's two variables here still. So what we're going to do then is we're going to take the equation for the volume of the can. We know that the volume is 500 cubic centimeters, and the volume is pi r squared h. So here we go, we can solve this for h. This value then is what we're going to substitute in place of the h right here. So when we do that, that gives us our cost as a function of r. The rest of this then we can actually find by using a graphing calculator. We need to find the minimum value of this function, and you can use your graphing calculator to do that. If you need help with this, we'll go over it in homework then on Wednesday because we've run out of time. So we'll stop now.